So thank you so much to the organizers for putting together this wonderful workshop, and also thank you for inviting me to speak and arranging the talk so nicely that that my collaborators spoke in the previous two talks. Anyway, more specifically, I'll be speaking about joint work with Arvind Iyer and James Martin, and this is building on our previous joint work with Sylvie Cortil and Olja Mandelstam. So by the end of this hour, everybody here is going to be an expert on multi-line queues and TASEP on a ring. Hope you're not sick of it yet. So the first part, I need to just review the terminology and notations for multispecies ASEP and also Macdonald polynomials and multi-line diagrams. And then I will introduce the t-PushTASEP, which is a T generalization of the model that Arvind just spoke about. And I'll explain what we can say about it, in large part using properties of Macdonald polynomials at q equals 1. Okay, and of course, feel free to interrupt at any point if you have a question. Okay, so you guys have already seen multispecies ASEP on a ring, but let me just remind you that in this model, we have n sites arranged in a ring, and we have n particles, each with a non-negative weight. And we take these collections of n non-negative numbers, and we arrange them into a partition, lambda. So this is a configuration of multispecies ASEP, and the particles, when you put them in weakly decreasing order, gives rise to the partition 3, 2, 2, 2, 1, 0, 0, 0. And we have, in this model, we have two adjacent particles swapping places at rate 1 or t. And whether you swap places at rate 1 or t depends on whether the heavier particle is clockwise of the lighter one. So over here, I have a 2, which is heavier than its neighbor 1, and 2 is clockwise of 1, so they swap places at rate 1. And on the other hand, over here, I have a 2, and its clockwise neighbor is 1, which is smaller, so they swap places at rate t. And so this is a Markov chain associated to every partition. S lambda is going to be my notation for the set of all compositions that I can obtain by permuting the parts of lambda. And S lambda is going to be our states for this Markov chain. Okay, and states are given by these compositions, and we're viewing compositions on a circle. Okay, so this is just more formally what is our Markov chain, what are the transition probabilities. Okay, this is the small example when lambda is 2, 1, 0. So we have 6 different states. And you can solve for the steady state probabilities, and you get these nice polynomials. And as has been mentioned earlier, the stationary distribution is closely related to Macdonald polynomials. Okay, so I think Olja already defined Macdonald polynomials, so I'll be a little bit brief here. Macdonald polynomials are homogeneous symmetric polynomials indexed by partitions. They're uniquely determined by an orthogonality property, and this property that when I write p lambda in the monomial basis, then it has this leading coefficient m lambda, leading term m lambda, when I order my terms in dominance order on partitions. This is one example of a Macdonald polynomial. And a few facts is that they generalize Schur polynomials and Hall-Littlewood polynomials. And there are also non-symmetric versions of Macdonald polynomials and some more general permuted basement Macdonald polynomials. Okay, and we're going to be talking about probabilistic interpretations, but as perhaps both both speakers may have mentioned earlier today, the starting point that inspired our work was the fact that we learned from a paper of Cantini, De Geer, and Wheeler in 2015, which is that if you take your Macdonald polynomial p lambda, you specialize all the x's to 1, you specialize q to 1, this gives you the partition function for the multispecies ASEP on a ring. Okay, so let me review the notion of ball systems and multi-line diagrams. So these objects were introduced by Ferrari and Martin and can be used also to give a formula for Macdonald polynomials. So a ball system is an L by N array of positions. Every position is either empty or filled with balls. So this is an example with L is 3 and N is 8. Yeah, I'm labeling my rows from bottom to top. We view it on a circle, so the rows wrap around. And now a multi-line diagram, which I actually normally I call it a multi-line queue, but James prefers the notation multi-line diagram, and he invented them, so I guess I'm trying to switch to multi-line diagram. So a multi-line diagram is for every row from 2 through L, a matching of balls from row R to R minus 1. And as we've seen in Arvin's talk, we should be thinking of customers and services with those in higher rows having priority. So this is how we can construct a multi-line diagram. Every ball B gets matched to a ball, any ball, B prime in the row below. And so we can connect them via the shortest strand that travels either straight down or from left to right, allowing wrapping around. Okay. So I'm allowing I'm allowing matchings to skip over balls below. I'm not forcing them to take the closest ball when they look from left to right. So we match all of our balls in the top row to some partners in row L minus 1. And then we match these partners to new partners in row L minus 2, and so on. And all of these balls that get matched in this process get labeled by L. Okay, and then we take any unmatched balls in row L minus 1 and we repeat the process. And one thing that's important to know is that if at any point I have a free unmatched ball B prime directly under the ball B that I'm trying to match, I have to pair them. So that's called a trivial pairing. Okay, so yeah, so this is just showing how I can construct a multi-line diagram from this ball system. So I've started by matching 3 to partners below, and then I have to take unmatched balls in the second row, and I have to start looking for partners for them. And this particular ball saw before I paired it, it had a ball directly underneath, so I had to pair it. And now I'm going to go to these unmatched balls in row 2, and from right to left, I'm going to start looking for partners for them. Okay, and then in the very last step, so at this step, I have paired the unmatched balls that were on this second row, and now I just have an unmatched, well, now I have an unlabeled ball in the bottom row, and that gets a 1. Okay, so this is a multi-line diagram, and the type of the multi-line diagram is the word at the bottom. So 2, 2, 0, 0, 0, 3, 2, 1. Okay. Okay, and then there's a QT weight that we can associate to every multi-line diagram, and we associate a weight to every pairing. So as we pair 2 balls, we attach to that line, pairing them, a particular weight, and the the weight of that pairing, what we're going to do is we're looking at how many balls get skipped over. And then we have a denominator that's taking into account how many balls there were to choose from when I made the pairing. And there's a Q statistic as well, which is actually not important in this talk, but is taking into account wrapping around the circle. OK. And then the weight of a multi-line diagram is going to be the product of the weights of all of its pairings. So that's giving me some expression in Q's and T's, times a monomial in X's, which is keeping track of how many balls there are in every column. So this factor here is the QT weight that I get by looking at the weights of all of the individual pairings. And then I get this monomial here by just counting how many balls there are in every column. So in column 1, I have 1 ball. In column 2, I have 2 balls. In column 3, I have 1 ball. So that's giving the x1, x2 squared, x3. OK. OK. So if we now let f mu be the expression in x1 through xn, q, and t, which I get by summing over all multi-line diagrams with bottom row mu and summing up their weights, this polynomial we're going to call an ASEP polynomial. And so a couple of facts about this polynomial. So suppose that lambda and mu are a partition in composition. So f lambda is going to be the non-symmetric Macdonald polynomial, E lambda. F mu, so the general ASEP polynomial, is going to be a particular permuted basement Macdonald polynomial. And the symmetric polynomial, P lambda, is going to be exactly what we get if we sum up all the ASEP polynomials, F mu, where mu varies over all compositions I can get by permuting parts of lambda. OK. OK. And also, this gives rise to a new proof of a result proved by Martin, which is that when you make this specialization as x's and q go to 1, then your steady state probability of being in state mu of our multi-species ASEP is f mu over z lambda. OK. OK, so this is an example. If you wanted to say compute the non-symmetric Macdonald polynomial corresponding to the partition 2, 2, 1, 1, 0, 0, what we can do is look at all multi-line diagrams whose bottom row is 2, 2, 1, 1, 0, 0, add up their weights, and that gives us the non-symmetric Macdonald polynomial. And then if you make this specialization, we'll get the steady state probability of being in state 2, 2, 1, 1, 0, 0. OK, so I'm going a little fast because Olia has already essentially mentioned the same.
I thought in Olia's talk you got some symmetric Macdonald polynomials by doing this exact thing.
So good. Thank you for asking. So if I want the symmetric Macdonald polynomial, I have to now add to this the similar quantity. So I have to let my bottom row vary over all permutations of 2, 2, 1, 1, 0, 0.
Oh, which Olia also said, right? OK. Yeah.
But thank you very much for asking. Any other questions? OK. All right. So OK, but now the question is, what if we want to keep x1 through xn general? And also, we want to keep t general. So we want to know how to find a probabilistic interpretation of these ASEP polynomials and Macdonald polynomials with general x1 through xn. And so Arvind talked about the case t equals 0, where the answer is a model called push-TASEP. And I'll review the definition of this, and then I'll tell you what is t-PushTASEP, so you can see how this is a natural generalization of push-TASEP. OK, so first we're talking about the t equals 0 case. So we're given a partition lambda then the multi-species push-TASEP is again going to be a Markov chain on S lambda, the set of all compositions obtained by permuting the parts of lambda. And now we're in a system where we have positive real parameters x1 through xn, and at every site, j, we have an exponential clock which rings at rate 1 over xj. And so, okay, so how does this work? If the bell rings at site j, so this is a depiction where my bell has rung at this site 2, then what happens so we first look, we see, do we have a particle of species greater than 0 here? So we have a particle of species 3 here. So this particle now becomes active, and it's going to move clockwise around the ring until it finds the next site with a particle of smaller species. So 3 moves around like this, 4 is bigger, 5 is bigger, but now 2 is smaller. So now 3 is going to come here, and it's going to displace this 2. Okay. So our 3 is going to settle at the place where 2 was, and now this new particle, the new particle of species R1, is going to become active, and it's going to now jump up and start looking around for the next smallest particle. And here it's going to find the next smallest particle is 1, and so 2 is going to settle at 1, and then this 1 is going to become active, and now keep moving until it finds something which is smaller, and it's going to find this vacancy and settle there. Okay, so the process ends when the active particle finds a vacancy, and now you can see that so our single transition goes from this state to this state. Our 3 has landed where the 2 used to be, so 3 is here. The 2 has landed where the 1 used to be, so 2 is here. And the 1 has landed in this vacancy, so 1 is here. And the particle who originally woke up first, this 3, this site j, is now empty. Okay.
Question.
Mm-hmm.
So I'm not very familiar with this, but from the definition of just ASEP, it looked like there wasn't a reason to need to have vacancies. And here you seem to need to have vacancies. Are we only looking at things that have vacancies?
Oh, I guess as I've described it, we need to have a vacancy, but you could always recolor, and you could always treat your or alternatively, you could always treat your smallest particle as a vacancy. Yeah. Other questions?
But even if there's no vacancy, like the 3 would have left, and then there would be a vacancy available for the 1 to fill in.
Say it again?
So if there was no vacancy in this picture, then it would still work, right? You could still the 3 would go away and then swap with the 2, and the 2 would swap with the 1, and the 1 would swap with the... So they would all move, but at the end, all the chairs would be taken.
Yeah, but here wouldn't we just be treating our smallest particle as the vacancy? Like that smallest particle would just go, oh.
Yeah, it would go back to
it would go back to the location.
Okay.
Yeah. Other questions or comments? Okay. All right. So now what's the t-PushTASEP? So this is a t generalization of the push-TASEP, but now every active particle can jump to any of the sites containing a smaller species. So now if we have k sites containing a smaller species, including vacancy, then our active particle will jump to any one of those sites at these rates. Okay, so it's going to jump to the first available site at rate 1 over t analog of k, and it'll jump to the second available spot at rate t over t analog of k, and so on. Okay, and crucially, the sum of these fractions is 1. Okay, so now in my example, our bell rang at site 1, so I've got a 1 over x1 in the rate, And now this particle 4, when it looked to find a place to jump, it could jump. So there's a 3 here. Sorry, the numbers are a little small, I realize. There's a 3 here, and there's a 2 here. There's a 3 here, and there's a 1, and there's a vacancy. Oh, did I? It has 1, 2, 3, 4, 5 available spots. So I think I actually should have had a t analog of 5 here. Sorry about that. And it jumped. It didn't go to the first available spot, but to the second, which is why I have a numerator of t. OK, but that's supposed to be a t analog of 5. And then this 2 is going to become active, and it has 2 possible spots it can go to, either where the 1 is or where the vacancy is. And so that's this denominator of t analog of 2. And it jumped to the first available spot. So this is a 1 over t analog of 2. And so I transition from this state to this state where now I have a, oh. Sorry, I think I also have a typo here. So this 4 became active. OK, so let's see. Oh. OK, I can change this. The good thing is I can change this. OK, so let's start correcting my slide. So first, this is a 5. This is a 5. And now, I don't even know how I managed to make this so wrong. All right, so this is supposed to be a vacancy. Now my 4 woke up and displaced the 2. So this is where 4 is supposed to be. And then my 2 woke up and displaced the 1. OK, so this 2 here is actually correct. And then the 1 woke up and displaced the vacancy. So that's where the 1 is. And this was always a 3 and stays a 3. All right. Do people agree? Yeah. OK, great. OK, sorry. All right. So now I'm trying to list some earlier references on things like t-PushTASEP, and my list of references is very much overlapping with Arvin's list of references. So there was work of Ferrari Martin on this discrete space Hammersley-Aldous Diaconis process. Leo Petrov studied the single type push-TASEP when t equals 0 on a half line. Borden Wheeler studied a multi-type t-PushTASEP on a finite interval. There's this frog model, and now we know about frogs with hats model. I'm probably missing other references here, and you are very welcome to tell me if there's certain references I should be adding here that are not here. There's a recent paper of Agarwal, Nicoletti, and Petrov relating multiple processes, including t-PushTASEP, to vertex models. So that's very interesting. OK. All right. So now what can we say about multi-species t-PushTASEP? So let's let lambda be a partition and eta be a state of the t-PushTASEP. So that means a composition obtained by permuting the parts of lambda. Then in the multi-species t-PushTASEP with content lambda and parameters x1 through xn, the stationary probability of configuration eta is exactly given by this ASEP polynomial f sub eta. And now all parameters are general except this q. This q is sent to 1. So essentially, our steady state probability is this ASEP polynomial, and the appropriate denominator is this Macdonald polynomial. So this gives a probabilistic interpretation of Macdonald polynomials and ASEP polynomials when q is 1, but the rest of the parameters are general. And then, of course, it follows. I mean, I defined ASEP polynomials in terms of generating functions of multi-line q's. And so we can compute these steady state probabilities in terms of the multi-line diagrams. OK. And Yeah, I should say there's been other work on ASEP polynomials, and in particular, there are matrix product formulas for things like for ASEP polynomials. And I think that's in the paper of Cantini, De Geer, and Wheeler as well. OK. And yeah, and these probabilities can also be computed in terms of vertex models. The paper of Agarwal, Nicoletti, and Petrov uses the Yang-Baxter equation, and they give a very nice, elegant proof of stationarity. But we use multi-line diagrams plus results on specializations of Macdonald polynomials and ASEP polynomials at q equals 1. So I'll say something about the ideas in the next couple slides. Any questions? OK. All right. So one idea that goes into it is that these multi-line diagrams are really encoding the t-PushTASEP dynamics, and at least in the following special case. OK, so I'm going to draw a picture to illustrate this. But the statement is that suppose we have a partition lambda with distinct parts, no entry equal to 1, and exactly one entry equal to 0. Then, if we have two compositions, eta and eta prime, obtained by permuting parts of lambda, the following quantities are equal. The probability of the t-PushTASEP transitioning from eta to eta prime when a bell rings at site j in state eta is equal to the following statement about multi-line diagrams. So, given a multi-line diagram with content lambda, such that row 2 has configuration eta, and the vacancy in row 1 is at site j, the conditional probability that row 1 has configuration eta prime. OK, this was a bunch of words, so I'm going to draw a picture.
Today is marking totally different.
Sorry?
Today is keeping track of something totally different.
Yeah, so let's see exactly how this works. So suppose that this is the bottom of a multi-line diagram. So this is my second row, and this is my first row. And let's just think about the rules for constructing a multi-line diagram and what that tells us we need to do here. So, so I'm always matching things based on highest to lowest numbers. So I'm first going to match this ball 8. And it has an available ball below, so it has to go straight down. Now we go to ball 7, and 7 has a vacancy underneath.
Sorry, did I say that out loud?
So 7 has a vacancy underneath. Let's say it like wraps around and joins up with that ball there, say. OK. Then in my multi-line diagram, my next largest number is 6. Has a free ball underneath, so it has to get matched downwards. 5 now also has a free ball underneath, so it has to be matched downwards. OK, 4 similarly, 3 similarly, and then 2, say, is next. It cannot be matched straight down because that number was already filled in. Sorry, I should have filled in these numbers here. 6, 5, 4, 3. OK, and now 2 is looking for a place to go. It matches here. But now how should we think about this? So how we should think about this is that we have a vacancy. We've got a vacancy over here. And that sort of like woke up in our PushTASEP, sort of woke up this particle here, which then moved around to this spot here displacing the 2, who then woke up and wound up like traveling to the vacancy. I don't know. Is this like reasonably clear? Okay. So so really the idea is that when you are in this special situation where we have a unique vacancy, and we also have no particle labeled 1, which is why the content of these 2 rows is exactly the same, then these 2 statements, these 2 quantities are exactly the same. Okay, so that hopefully gives some intuition for why multi-line diagrams might be related to this t-PushTASEP. Okay. Another useful idea is the idea of recoloring. So if we were to relabel particles while weakly preserving the order of the labels, the resulting system is still going to follow the t-push dynamics. So, if I have some weakly order preserving map, one example is that, let's send 4 and 3 to 3 and send 2 and 1 to 2 and map every other integer to itself. If I do this kind of recoloring, then just to draw some picture, like, I don't know, 4, 3, 3, 2, 3, 1, 2 or something. And now if I recolor, 4 and 3s both map to 3s, 2s and 1s map to 2, then the dynamics on the right-hand side is going to look just like the dynamics on the left-hand side. Okay, so that's something that is very helpful. And now there's analogous properties that hold for Macdonald polynomials at q equals 1. So let me first say it in a special case. If I have 2 composition, so if I have a partition lambda tilde and a composition eta tilde, and they have the same relative order as a partition lambda and a composition eta, then this ratio of polynomials, and this is the ASEP polynomial over the Macdonald polynomial at q equals 1, these ratios of polynomials is exactly the same. So just as an example, like if my partition is 7, 5, 3, 1, 1, and I put in my numerator some permutation of these entries, 5, 7, 1, 1, 3. So if I look at this ratio, and then I compare it to this ratio, and I've gotten the right-hand side from the left-hand side by just doing some order-preserving map. So 7, 5, 3 goes to 4, 3, 2, 1, 1, and 5, 7, 1, 1, 3 goes to this 3, 4, 1, 1, 2. Then these ratios of polynomials are the same. So this is something that is true at q equals 1, but it fails if q is not 1. And there's a refinement of this property. So my example over here, I took a sort of strictly order-preserving map, but there's a way to write down an analogous statement that works with a weakly order-preserving map, which is as follows. So say I have a weakly order-preserving map from natural numbers to the natural numbers, and let's let lambda be a partition and mu be the partition obtained by applying this weakly order-preserving map. So now, say I define this quantity g sub eta by summing up all the ASEP polynomials f sub zeta, where zeta is obtained by taking a permutation of the parts of lambda, such that the order-preserving map maps zeta to eta. So then I claim that these 2 ratios are the same. So you can think of this as, this is a generalization of the statement above, but it's a little bit more complicated when we work with a weakly order preserving map, because now there's going to be multiple compositions over here that map to, there's going to be multiple compositions that map to a given one under a weakly order preserving map. Okay, so here's the small example. Phi is the order preserving map mapping 1 and 0 to 1 and 2 to 2. Now, what I'm saying then is that this ratio, so here's my Macdonald polynomial 2, 1, 1, and this is the ASEP polynomial 1, 2, 1. And now what I'm putting over here is a sum of ASEP polynomials indexed by all compositions which map to 1, 2, 1 under phi. So what maps to 1, 2, 1 are exactly, so I'm mapping both 1 and 0 to 1. So we have 0, 2, 1 and 1, 2, 0. So anyway, so this is the appropriate analog of this statement up here. Okay, so this is so this is really the kind of Macdonald analog of recoloring for the t-PushTASEP. Okay, all right. So so I can mention a few other results that we get on multi-species t-PushTASEP. So there's a result about current between two adjacent sites, and this is for single species t-PushTASEP, and it has this nice formula in terms of elementary symmetric polynomials, with an interesting factor on the left, which is the t analog of the number m0 minus 1, and this is the derivative of the t analog of m0. And to prove this, we needed a lemma, which we haven't seen in the literature, but maybe somebody here has. So anyway, here's some lemma about elementary symmetric polynomials. If you've seen it, then please give us a reference. Anybody seen that one? Okay.
Sorry,
Yeah?
there was an elementary textbook on symmetric functions. It has pretty interesting exercises. Maybe browsing through that.
Which textbook?
Oh, look it up. Sorry.
Oh, okay. Great, thanks.
But this is also a derivative, right? This equality is if you take t to some power and sum up over all, so h is anything, right? Or
Yeah,
sum
h
up
is
with
just
t to the
something less
h.
than m0.
Yeah, so then the left hand side is like the coefficient in the derivative or something like this. I mean, what's the infinite series that corresponds to this? Anyway, I don't know.
Yeah. Okay. Anyway, if someone does know reference, we're happy to have one. I mean, it's not like a terribly important statement, but we're happy to have a reference if there is one. Another result is that okay. So suppose O is some observable, so an event or a random variable, and let's write brackets O for its probability or expectation in the stationary distribution. And then a corollary is that suppose k is a number less than n, let O be any observable in the stationary distribution of multi-species t-PushTASEP, which depends only on the configuration in sites 1 through k, and then this expectation of O is symmetric in the parameters xk plus 1 through xn. So Arvind mentioned a similar statement in the t equals 0 case, but I think not requiring stationarity. Here we need to require stationarity. And in particular, this result uses a kind of a key lemma that we needed in the paper with Sylvie and Olia, which is that for any composition eta, the sum of these two ASEP polynomials is symmetric in xi and xi plus 1. And I think in Olia's talk, Ben asked about whether it's easy to see that the expression for Macdonald's is symmetric. And one could get it using this lemma. This lemma is talking about sums of two f's. We get our whole Macdonald polynomial by summing over all f's. But anyway, one should be able to prove it using this lemma. And now I'm asking a question which was asked by Ben in the previous talk. Can we generalize t-PushTASEP to put the Q for Macdonald polynomials into the model? We do not know. It does not look very obvious how to do so. And in particular, our proofs very much used the fact that Q equals 1, like these properties for Macdonald polynomials having to do with applying weakly order preserving maps, like they just fail if Q is not 1. Anyway, that doesn't mean that the answer to this question is no, but it means that it's not so obvious what to do. Okay, and now I just wanted to sort of take advantage of having people here. So there's a variant of ASEP called the doubly asymmetric simple exclusion process, introduced by someone named David Ash, which Yuhan Zhang has been working on. And we've seen this one paper of David Ash, and we do not know who David Ash is. There's like a unique paper of David Ash on the archive, and it gives a Stanford affiliation. We cannot find a web page for him anywhere. We don't know if he's an undergrad or like some retired person, or like no idea. So if anybody knows who David Ash is, please let us know. And this is connected to a variant of ASEP called doubly asymmetric.
He's not affiliated with Stanford. Oh. He works in the industry, and he tries to attend virtual seminars.
Oh. Okay. Okay. We can talk after. Thank you. So just as a summary of what we've seen, we can compute steady-state probabilities in multispecies ASEP and t-PushTASEP using ASEP polynomials and Macdonald polynomials. And in the first case, we have to make the specialization all the x's and q is 1. And in the second case, we make the specialization q is 1. And these polynomials can in turn be calculated by multi-line diagrams. And so thanks very much. And these are the two references for the work I talked about.